Hi, this is Ms. Kang. Welcome to Algebra 2, Lesson 6-4, Logarithmic Functions. In this lesson, you'll be able to graph logarithmic functions and find equations of the inverses of exponential and logarithmic functions. Let's start with explore and reason. Compare the graphs. We see three different graphs. Which two graphs represent the inverses of each other? Explain. And we're going to explore the relationships. So what is an inverse? So we already talked about inverse functions in previous topics or in Algebra 1. So inverses are basically when your domain and range are switched, right? So when x is equal to y, that is your inverse. So by graph, you're going to see the inverse functions when it is reflected across the y equals x line. So if you draw the y equals x line on the first graph and reflect it across this line, you will probably have something like that. So that looks very similar to the second graph. So these two functions are actually inverses. Yeah, I didn't graph this accurately, but you have to reflect it to this line where, oh, that's the same point, but it's gonna go a curve over here, and then this point is like corresponding to that point, and so it's gonna go like this, and then it's gonna go like that. So if it's reflected across this line, all the points are equal distances away from this line, right? So like that. So if you graph a reflection across y equals x line, that is the graph of the inverse function, which means these two graphs are inverse functions. So let's record our responses. The two graphs on the left are inverses of each other. Explain. I'm going to move to a bigger space here. Yeah, so y, looking at the two graphs, looking at the first graph, it has points, which is -1, 1, 0, 0, and 1, 1. And the second graph has points 1, -1, 0, 0, 1, 1, which are inverses of each other. So x and y are flipped, right? And if you look at the points here, you have 0, 0. That could maybe be switched, but you have -1, -1, and 1, 1, and it's not inverses of any of these two. So if you look at specific points, you can explain it algebraically. Let's look at part B. What is the relationship between the domain and the range of the two inverse relations? So by definition, inverse functions have domain and range flipped on the opposite on the opposite side, right? So the domain on the left on this first graph, which is all real numbers, is the same as the range of the second graph, which is all real numbers for the range, which is not a function, by the way. And the range for the first one, which is greater than equal to 0, is the same as the function on the right, which is the same as the domain of the function on the right, right? So let's say that the domain of the first graph, which is all real numbers, is the same as the range of the second graph. the range of the first graph, which is numbers greater than or equal to 0 is the same as the domain of the second graph. Okay, there we go. So we have looked at the graphs of the inverse functions. Let's think about this lesson essential question. How is the relationship between logarithmic and exponential functions revealed in the key features of their graphs? So in example 1, we're going to identify key features of logarithmic functions. So graph y equals log base 2 of x. What are the domain, range, x-intercept, and asymptote? What is the end behavior of the graph? So first, we're going to create the table of values for y equals 2 to the power of x. Why? Because y equals 2 to the power of x are inverse functions, and you can rewrite them in different forms, right? 2 to the power of y is equal to x. But it's an inverse function, so if you switch x and y, you'll be able to get y equals 2 to the power of x, right? Let me write that down. So this, in another form, is, in exponential form, is 2 to the power of y equals x in exponential form, right? So the inverse function of this one should be 2 to the power of x equals y. So this is the inverse equation of this, right? So y is equal to 2 to the power of x. And then you're going to, because this is easier, we already know 2 to the power of x. And then you switch x and y to get the, values for log base 2 of x, because there's no way you can do this by hand without this scale, right? So if you don't have a calculator, this is the method you have to use to graph log functions. Think about it as an exponential function, and then use the inverse of that. So graph the ordered pairs. You can graph them one by one. You'll be able to get this nice little curve. That's the exponential function. This is the log function. And notice that they are the reflections of each other over the line y equals x. This line, right? Beautiful. So the domain for your exponential function is all real numbers, but that would be the range of your log function because it's the inverse, right? The range of the exponential function is all positive, so anything greater than 0, which is the domain of your logarithmic function. Because they're inverses, domain and range will be swapped. And then the x-intercept would be 1 instead of the y-intercept you have for the exponential function. So the x-intercept will not be there for the exponential function, but you have the x-intercept for the log function, but you don't have y-intercept for the log function either, because there's a vertical asymptote instead of the horizontal asymptote for log. So the asymptote is x equals 0 or the y-axis. And the end behavior, as x approaches 0, y approaches negative infinity, right? So that's the first arrow here. And then this behavior, this end behavior is when as x approaches positive infinity, y approaches positive infinity, very slowly, logarithmically. So let's look at try number 1. Graph each function and identify the domain and range. List any intercepts or asymptotes. Describe the end behavior. So pause the video, see if you can solve it by yourself. Come back when you're ready for answers. Okay, are you ready? So let's look at part A. This is log base e x, right? So in exponential form, you have e to the power of y is equal to x. So this one, you can use your calculator because e is like pi, where it's an irrational number, and so you can figure it out using your calculator. So you can make a table of graph. You'll see that when x is -2, natural log will be undefined. So -1, 0, they're all undefined. But then if you have a fraction, say 0.1, you have -2.3, 0.5 will be -0.69, and then 1 would finally be 0, and then 2 would have positive number 0.693147, 3, 1.0986, 4, 1.386. So then you can graph using some of these points. So 1, 0 is your x-intercept. This is definitely important. 2, 0.6, 3, 0.6 is very low, right? And then 1.09, so it's going to go like that, and then the other way is going to go to negative infinity, but it's you have a vertical asymptote at the y-axis. Okay, let's identify domain and range. So this is the graph, and then domain is all real range is all real numbers, right? Domain would be anything greater than 0 and not equal to 0. And range is all real numbers. X-intercept is equal to 1. Asymptote is the y-axis, or 0. And then the end behavior, as x approaches 0, y approaches negative infinity. And as x approaches positive infinity, y approaches positive infinity as well. Okay, so that's part A. Let's look at part B. This one is the same way. So if you change this to exponential form, it's going to be 1/2 to the power of y is equal to x, right? So your inverse function, so this is the same, actually, yeah. So this is the same as, if you change it to inverse, you'll be able to have 1/2 to the power of x equals y. And you can find the table of values for this one easily, and then switch x and y values to get the graph of your original function. Remember, this is the inverse. Okay, so if you do that, you'll have the table of values with -1 and 0 still undefined, and then 0.1, 3.32, 0.2, 2.32, 0.5, 1, and then 0.7, 0.51, and 1, 0, 2, -1, 3, -1.58, 4, -2, 8, -3, and so on. So then you'll be able to graph this using some of the major key points. So your x-intercept is at 1, 0, 2, -1 is a nice little whole number, 4, -2, and 8, -3 as well. And then all the other end behavior, you have a horizontal asymptote over here, and this between 0 and 1. When x is between 0 and 1, your y is approaching positive infinity. Okay, so that's the graph. That's the approximate graph. Okay, 1, 2, 3. 1, 2, 3. Let me label that. And then your domain is anything greater than 0. Range, all real numbers. And then x-intercept, 1. And then the asymptote, the y-axis, or x equals 0. And the end behavior is as x approaches 0, y approaches positive infinity, right? As x approaches positive infinity, y approaches negative infinity. Okay, that was a big try it number 1. But check your answers, see if you got it right. If you did, good job. This is very important because it is very conceptual. It requires a conceptual understanding. And yeah, conceptual understanding is key to solving other problems. Let's look at example 2, graph transformations of logarithmic functions. So now that we have log, can we apply transformations for this as well? Of course we can. So for log functions, all the transformation rules apply. So your transformation function g of x will look something like a log base b, where base should be the same, and then x minus h, and then all of that plus k. Okay, so if you look at this function, log base 2 of x plus 3, you know there's a horizontal translation, right? 3 units to the left. So your original f of x, which is log base 2x, it looks like this. That's a blue line. That's a blue curve. And then from here, you're going to go left 3 units. So 1, 2, 3. Your x-intercept moves 1, 2, 3. All your other points move 1, 2, 3 to the left. Okay. And so that's it. And because your h has moved, your vertical asymptote also moves 3 units to the left. So now instead of the y-axis, you have a vertical asymptote over here. Okay, so yeah, this for logarithmic functions, because it's an inverse function of an exponential function, it is going to have opposite properties, opposite characteristics. So remember, your exponential function had horizontal asymptote, and if you moved up or down, so depending on k, you will move your asymptotes. But here, this is exponential function. Your log function will have the horizontal translation that will move your vertical asymptotes left and right, right? Okay, so let's look at try number 2. Describe how each compares to the graph of the parent function f of x equals natural log x. So pause the video, come back when you're ready for answers. Okay, are you ready? Let's look at 2a. So we have natural log x plus 4. So from your parent function, we added k equals 4. That means we translated where? Up 4 units. And that's it. Part B, 5 times natural log x. So we have that 5 multiplied to your parent function. So this is a vertical stretch of 5. If you're not sure why, you need to go back and review the transformations of other functions that we looked at pretty much every topic. And the first transformation is in topic 1. So you can go back to that lesson to review. But let's look at example 3 now. Inverses of exponential and logarithmic functions. And now let's look more into the inverse relationship of the exponential and log functions. So what's the equation of the inverse of the functions? So for example, if we have f of x equals 10 to the power of x plus 1, you're going to change x and y and write the inverse function for y, right? So this is your original form, and then you switch x and y, and then you solve for y. And that's going to be your inverse function. So you can write it as this notation. F and then -1. That's not a power, but this is called the inverse function notation of x is equal to log x minus 10. Okay, so if we start with log base 7 x plus 5, the inverse function for this one would probably be exponential, right? So change x and y. And then here you need to solve for y. In order to do that, you can change the form to exponential form. Base 7 to the power of x is equal to y plus 5, right? And then you solve for y. You just subtract 5 on both sides, and that's going to be our inverse function. So now it's your turn. Try number 3. Find the inverse of each function for parts A and B. See if you can do it by yourself. Pause the video. Come back when you're ready for answers. Okay, are you ready? Let's look at part A. So you're going to switch this to y equals 3 to the power of x plus 2 and switch x and y and solve for y. You're going to change this to log function. So log base 3 of x is equal to y plus 2. So y is equal to log base 3 of x minus 2. And that is your inverse function of f of x. So rewrite this in the function notation. Okay, part B, do the same thing. Instead of, I'm gonna skip step and just change x and y right away. So this would be your inverse function, solve for y. Before you change it to exponential, you might want to add 2 on both sides, right? And then change it to the exponential function. 7 base 7 to the power of x plus 2 is equal to y. And that's it. So f of -1. So the inverse function would be 7 to the power of x plus 2. Okay, good. So that's how you write the inverse functions. Let's go to example 4, interpret the inverse of a formula involving logarithms. So a company uses this function to relate sales revenue R and advertising costs A with this equation. So what's the equation of the inverse of the formula? Which equation would be easier to use to find a value of A for a particular value of R? Obviously this equation is written in terms of A for R. So if we have a given A, then it's easy to calculate for R, right? But obviously if we want to find the value of A, right, for a particular value of R, that means we're plugging in R. So R is the input and A would be the output. In that case, we need an inverse formula, and that would be the easier formula. So in this case, we're not going to change this equation, but because the company uses this function, right? We don't want to change the function and find the inverse where R and A are switched, right? So instead of that, we're just going to solve for A. So this is going to be solving for a type of problem, but they kind of look like they look like inverse functions because we need to use inverse operations to solve for A, basically. So you're going to subtract 25 on both sides and then divide by 12. And then now we're going to change it to the exponential form and solve for A, which is 10 to the power of R minus 25 over 12 as a power minus 1. So the inverse formula actually did not interchange A and R, but when we solve for A, this is the inverse formula. This is also called the inverse formula in the real world scenario. So that may be a little bit confusing. You can look at the look at the situation and see if that's appropriate, right? So you always have to think about it. Yeah. So it will be easier to use the inverse to find A when R is unknown. So let's look at try number 4. Describe what happens to the amount of monthly revenue as the cost of advertising increases. How might you determine the optimal advertising budget? Explain. So this one, actually, we could answer right away. Because we have already figured this out, right? We already figured this equation for A. We know that R is going to be we know R is the revenue and A is the advertising cost. So I think it'd be better if we can graph it, if we would be able to graph this function. So we're going to graph the R function, right? So your f of x, which is just basic log function, will look something like that. That's a very bad function, but this is assuming this is the correct f of x function. Let me do it again. Let me try again. So there's 1, 0, and then you have a vertical asymptote here. Your R is a horizontal, it's vertical stretch, and then you add 25, right? And then you have a horizontal translation of -1. So -1 here, add 25, that's, 25, and then vertical stretch. So it's gonna look something like that. So in this case, what happens to the amount of monthly revenue as the cost of advertising increases? So as this is A, because we're graphing R. So R is Y, A is X. Whereas A, so disregard, this is the parent function. Okay, this is the function R. So as monthly revenue, as the cost of advertising increases, as A goes greater, we're looking at this end behavior, the revenue would increase, right? It wouldn't increase exponentially like that, right? But it increases slowly, as a logarithmic function would do. So we can say it increases logarithmically. And so let's explain further here. So as the amount of advertising increases, the amount of revenue increases logarithmically. You can determine a target amount of revenue and then use the model to determine how much to spend on advertising to reach that target. Okay, good. So let's look at the last example, example 5, compared to logarithmic functions. Logarithmic functions can approximate the altitude of a plane over time, which plane altitude shows a greater rate of change over the interval 10 to through 15. So here's plane A with this equation. It's a natural log equation. Here's plane B with a graph, but this also follows on logarithmic behavior, right? So first, we can determine the average rate of change for plane A for the interval 10 to 15. So you get the point for 10 and 15, so minimum point and the maximum point. And then you find the slope, that is the average rate of change for that interval, right? So 10, 31,184 is a point here, and 15, 34,914 is a point here. For here, 10, this one, we have this points already, this and that. So using those values, we're going to find the average rate of change by the slope formula. And then we see that plane A has far greater average rate of change than plane B. So between 10 and 15 minutes after takeoff, the average rate of change of the altitude of plane A is greater than the average rate of change for plane B. So let's look at try number 5. For which plane do you think the altitude will change more quickly over the interval t greater than or equal to 15 through 20? Explain your reasoning. So we already talked about the average rate of change. So use this. See if you can explain this by yourself. Pause the video, come back when you're ready for answers. Okay, so which one would change more quickly? Would plane B eventually go more quickly than plane A? Well, I don't think so, right? Because they're both logarithmic function, as I mentioned before. So then they're gonna have the same behavior, like it's going to increase logarithmically, very slowly, right? So in this case, plane A increase at a greater average rate than plane B, right? Between 10 and 15. So since both of the same model, they're going to plane A will continue to increase as a greater average rate. Yeah. So why don't we record that? Plane A increased at a greater average rate than plane B between 10 and 15 minutes after takeoff. And since both follow a logarithmic model, plane A will continue to increase at a greater average rate. Okay, good. So that was it. That was our lesson. So let's summarize our lesson. We learned about logarithmic functions. So we looked at the characteristics of logarithmic functions and looked at the inverses, the inverse relationship between the log function and the exponential function. Please keep in mind that the key features for log function and the exponential function would have inverse relationship between the domain and range, right? And so the x-intercept and y-intercept would be the same, and the asymptote would be also the inverses. So these are very important to notice. The end behavior will also be inverse to each other, and the graph will look like they have a reflection over the y equals x line. Okay, so that was lesson 6-4, logarithmic functions. Thanks for listening. We'll continue with the next lesson in the next video. Bye!